Okay, good afternoon, everybody. On behalf of ATP Hydropower, I would like to welcome you to that webinar, Boosting Hydropower Beyond the Project. It's the fourth edition of this series of webinars, so we are very pleased to have three speakers this afternoon who will present us, I would say, very important and very successful European projects, which came out recently or 2 years ago with very good results, which are now used widely already in the hydropower sector. So I think we just have a look on the agenda. So when you show the next one. So we, as I said, we will have a presentation of these successfully finished 3 European projects. And of course, at the end, we will have a short discussion on the outcomes of this project. I will start first with a short introduction on ATP Hydropower, who organizes this webinar. So if we go to the next slide. So, we thought that ATP Hydropower in principle is a project which followed the Hydropower Europe, and Hydropower Europe has prepared, I would say, a very important research and innovation agenda, together also with a strategic industry roadmap. And we have produced a small YouTube, I think, which gives quite a good overview on the needs of research and innovation, as well as strategic action in Europe to bring forward hydropower. So I hope we can later on this video.
Yes, with the video we are having some issues with the audio, so we will forward to you the video so you can see it and watch it afterwards. We will move forward with this, and if we get to solve the video audio, we will go back to you and play it afterwards.
Okay, so that we will just share afterwards the link, and everybody can see this video, which I recommend to everybody, where you can really see a little bit in which direction we should go. All these 3 projects which we will have a presentation today are already in that direction. So ATP Hydropower will enhance and disseminate better, let's say, this research and innovation agenda, as well as the strategic industry roadmap. And we have started about 2 years ago, a little bit more than 2 years ago. We have started to consolidate the strong network, which we have already, which achieves today some 1,000 stakeholders. So we are in this way, we are very satisfied. And we would like to help in future to unite Europe. We can go to the next one. So the intended role is to help and unify and to amplify all initiatives which already exist. You see that with that anchor image. There are quite a lot of initiatives in the hydropower sectors, which are mainly association, mainly on national level, some on international level. And with our ATP Hydropower, we would like to, let's say, to help to unify this sector by presenting a single voice on certain key issues. Of course, we are focusing mainly on research and innovation and strategic actions. Of course, we do not like, or we will not duplicate any role of existing groups, but we would like to enhance. At the end, it's important that the message go up to the policymakers. We are already working with Hydropower Alliance, which is gathering 10 large producers of hydropower in Europe. So we go to the next, Iraya. So hydropower, ATP Hydropower, we are under action since almost 2 years. We have an operational structure in place, the secretariat. We have also an industry-driven governance with all stakeholder sectors and a widely open scientific advisory board, which are 26 members. You see here some names. Myself, I'm chairing, or let's say from the scientific point of view, coordinating the project. Then we have a governing board chair, Denis Albrecht, and we have governing board co-chairs Antonella Frigerio and Peter Stegner. I think perhaps they are all online, or some of them are online. What could interest you? We have established the so-called HERI platform, which should give information on ongoing and already finished projects on the European level, but also on the national level. So the structure of this platform is ready, so you can see them on our website, and we are at the moment still trying to get much more information that we already have. That means to convince a lot of people who are involved in project also on national level to give information on their project. Let's go to the next slide. So we have 4 working groups. We are very satisfied that there was a huge, let's say, motivation of many people to participate to these 4 working groups. So we have one on hydropower role for flexibility and storage, and a second one, hydropower and biodiversity, hydropower and climate change, and the cross sectorial working group, which wants to promote and disseminate an uptake of past, current European R&I projects, which in principle is the purpose of this webinar today. First results of these working groups will be presented during our Hydropower Day, 8th of April, which I will just present you a slide at the end. And let's go to the next one. So this webinar is organized by this cross-sectoral working group. Our scope is, as I said, we follow up the Horizon project related to hydropower. We want to inform regularly on this project progress and results. And we still try also this year to motivate and facilitate the organization of a special session at conferences. We try to bring that to reality during Hydro 2025, which will take place in Thessaloniki in Greece. So we will contact all contacts we have to this European project to see if we can bring together a kind of a special session, which I think would increase the visibility of this project also to the professional field of hydropower, knowing that this hydro conference, normally there are 1,500 people attending from the sector. So the next slide, perhaps. So I'm just coming to the end of this very short introduction. As I already said, you can find information on our website. We are also active on LinkedIn. And we normally do on certain topics consultation. As I already mentioned, we have about 1,000 consultees or stakeholders registered, which we contact regularly with information and also asking them to give us a feedback on certain questions. So now the next, and I think that will be the last one. Yeah. So now we come, let's say, to the core of this webinar. So I'm happy to present you the first speaker. So Atle Harby, he's a senior research scientist at Sintef Energy Research in Norway. So he has 30 years of experience in hydropower and river regulation. His work focuses on environmental impacts, energy system, water resources, and climate change. He has published many papers. He contributed also to the IPCC and IEA reports, and probably you know him also from popular science articles which he has written. He was a work package leader in Fit Hydro, which the project which he will present today. And actually, he coordinates the new EU project ReHydro for the next 4 years. Atle, thank you very much. And I give you the floor.
Thank you very much. Let me see if I can present. I think so. I'll just share a window. Yes, sorry. Okay. Are you seeing my slides now?
Yes.
Yep, we see them.
Okay, thank you. Yes, I will present the Fit Hydro project. It's an abbreviation for fish-friendly innovative technologies for hydropower. And I'll go briefly through some of the key elements and key findings and key results, which, as Anton said, are now widely used, I think. We have the 26 partners, half of them from research and half of them from industry, representing 10 countries. And the goal of Fit Hydro was actually to develop cost efficiency, environmental solutions for hydropower and to maintain also hydropower generation or even improve. So trying to improve both the environmental conditions and the hydropower generation. And of course, we should present a lot of decision support tools and what we call the solutions, methods, tools, and devices. We had a lot of test cases around in Europe, in several countries, and to actually apply and test out those innovative solutions we were finding. We had about 7.2 million euros in budget, and something like, I would say, at least 20% extra of that as some kind of own funding and among partners. The project was supposed to end, I think, actually during the COVID period in late 2020. We were then still hoping to have a final seminar in person, but of course, as you all know, this was quite difficult in 2020 and 2021. So we all ended up with a webinar as the final solution. But there's a lot of things left back from Fit Hydro, which I'm gonna show you now. Just some photos of all the things we were looking at and typical challenges at hydropower plants for fish then are the migration, because we block it with our dams and devices in the river, and looking more detailed into, for instance, things like the function of fish ladders, the entrance of fish migration solutions, and also more detailed a survey of how fish behave and their swimming paths. Maybe more challenging.
Sorry, Atle, I see only a part of the slide. Is it only me or the others too?
I don't see what you see. I just see my screen, and
for me it's actually the same. I don't know.
Yeah,
if you can zoom out the presentation a bit.
So yeah, perhaps you just put full screen or go out again and put full screen, or
okay.
Yeah. What about now?
Now
it's perfect. So we can see all the fish. That's important.
Okay. Yeah, I'm sorry. We used to use, actually during Fit Hydro, we used this GoToMeeting and GoToWebinar all the time. It was a very good tool. So I was used to it then, but since then we only use Teams. So I'm sorry if I'm unfamiliar with how to use it. Okay. Yeah, this one you need not see perhaps, but I'll skip that one anyway. I told you about it. Okay.
I think that's okay. We saw the important part. It's perfect.
And this one you see the full screen from a little photo of an entrance to a fish ladder in the lower end. Yeah, good. Okay. Yeah, so it's going to be some photos of what we did, and you also see some devices here and people mounting things to track fish and so on to actually look into the challenges of making sure that fish can pass upstream and also downstream, which is maybe even more difficult because of the ability to most of the flow will have to go into the turbines, and we have to get the fish to go somewhere else to not be chopped up, so to say, inside the turbines. So I'll come back to some of the devices we developed to do this, but we had a look at guidance efficiency and attraction to the bypass, and also looked into how fish, what would happen to fish if they actually pass through the turbines. Other challenges with hydropower and fish is, of course, that we modify the flow and hence impact their habitats, both all kinds of habitat for spawning, for rearing, for adult fish, and how it's distributed and how much water we deliver to the bypass reaches of hydropower impacted rivers are quite crucial. So we did both modeling and also field work to actually test spawning gravel or to see how habitat conditions change with flow. We also had a special focus on hydropicking. I'll come back to that as well. We also had a little bit of focus on sediments, because we all know that also dams stop sediments and block it, which will eventually have a large impact on the downstream river and downstream fish habitats, maybe changing the substrate conditions and so on. So we also looked at solutions to make sure that actually the geomorphological processes keep on going as they should be. Okay, that was a little overview of the main actually challenges with fish and hydropower. And I'll explain some of the tools and methods we actually developed in Fit Hydro. You see here a long list of solutions, methods, tools, and devices that can help investigate how the conditions are at hydropower plants and look for solutions. I'm not going to explain all of them because that would take too long time, but you can read about all of them in the Fit Hydro wiki, which is still working. It's an open access online platform. It's not really a wiki in that order that everybody can edit it, but those who were members of Fit Hydro could. We have divided this wiki into what the main challenges are, like I showed you just now on habitat and e-flows, upstream and downstream migration, and sediment. So you can enter the wiki in many ways. If you have a challenge or think you have a problem, you will find what are the tools, what are the methods you can use to investigate, to find out the problem and to solve it with mitigation measures. So it's kind of a systematic built up wiki or web page where you can find a little bit of information, and if you click further down you'll find more information, and you can link up to references and even hopefully, I think, find those contact persons that actually were developing the tools or took care of it. These will help in the whole phase of hydropower development and planning, implementing, maintaining, and monitoring these measures to see their success rate and so on. And all of these solutions, method, tools, and devices were tested in different test cases of Fit Hydro. So some of them were also in a prototype status before we started Fit Hydro, and some has even been developed a little bit further after Fit Hydro, but they are live solutions. One example of things we did was the barotrauma detection system, which actually consists of a little instrument like the like this instrument here. You see, it's a sensor that is quite rugged and can withstand pressure and heats being sent through a turbine to log, and there are sensors in here, accelerometers and pressure sensors that would tell you what would happen eventually to a fish that goes through a turbine. It's only 10 centimeters long, and it has this system of a balloon, which you see on the right-hand side, that it has no buoyancy, but when it comes through on the other side of the turbine, this balloon will inflate and it will come to the surface. So the trick is to be in a boat or on shore or something downstream the power plant and retrieve these points. And you see in the middle a little figure of what happens when you pass through a turbine going downstream. The the black line is recorded the upper and lower boundary of using these BDS sensors, and you see there is a large pressure drop which can be harmful to fish if it's too rapid variations here. You also record any hits from turbine blades and so on, so you can actually get an idea of what would happen to a fish. We have this was developed by Tallinn University of Technology, and we have actually used it in Norway and in Sweden from SINTEF, and with quite good success. The only thing is that we lose a couple of sensors every time, and the cost of one is 1,000 euros. So you have to take care of that. However, we put a telephone number on them, and we have retrieved several of them from people who found them further downstream in the river later on. Call us and we'll give you a finder's fee, so it's possible to retrieve it. And then you also get some data back, actually. Quite interesting. Another thing we did was through a lot of laboratory studies, we developed this curved bar rack bypass system. It was developed by ETH, and it kind of provides better solutions to guide fish to the right bypass instead of getting them into the turbine with a better efficiency on the fish and with less head loss. That was kind of the main advantage with this system, and we actually proved that it has 4 times lower head loss compared to the normal shape of the bar rack in front of turbine intakes, and it has been tested with different fish species as well. So it's quite impressive performance and suggested to be. I think it's now installed somewhere. We had from beforehand a lot of focus on in several countries and national projects on hydro peaking impacts from power plants that are turned on and off, leading to rapid changes of flow in the downstream river. So we developed kind of a framework, we call it the hydro peaking impact assessment tool, which can use either flow records or synthetic flow records, field measurements, or modeling to describe the physical conditions, and hopefully also fish population data that you can tell something about how vulnerable the fish population is. And then this tool investigates rate of change, rate of frequency and timing of water level and flow fluctuations, and also the changes in habitats to actually give you a, combined with the vulnerability of the fish populations, to give you a score on the impact, like you see on the right-hand side here, from where you combine actually the effect of the peaking and the vulnerability of the fish. And the goal of this is, of course, to try to do things that you can move from the upper red left corner down to the green corner, where actually hydro peaking would have a very, very small impact. We also made several decision support systems or systems to help make decisions. So it's kind of a screening tool, evidence-based decision-making to find the mitigation measures and first of all the impacts on fish. And it's kind of a screening tool on more like a high level to find out what actually are the potential risks here and how to make decisions on what to focus on to improve conditions. So it's an online tool that is still alive. And you see from the diagram, I'm not going to explain it, but it has several inputs, mostly from also research done in Fit Hydro to actually find your way. And it's also linked to the Fit Hydro wiki, so you can really find what would be the tools and the mitigation measure you should do if you have this and this problem. Another tool, which is a bit similar, but simpler in the way it's really addressing fish hazard and risks of turbine passage, up and downstream migration, and flow alteration that may impact fish. So it gives you a risk score, and if it's a high risk score, if it's kind of fish species that are very sensitive, shown on this graph, and a high hazard, it will kind of show you where you should perhaps do more investigations to solve these kind of problems. The input data you need are some specifications on the power plant, some flow measurements, flow statistics, and some of the possibilities of where can fish move downstream and upstream, and the facilities, and of course some fish data. This is developed like an Excel tool, which is also available for anyone. And we'll give you kind of a score. As you see here, some green and red. I'm not going to explain it, but you will have for each of the fish species some kind of green, red, or yellow indications. And you should, of course, go and look more into those red ones. That's where you can focus your mitigation measure. We did not only look into technical things, we also looked at some social acceptance of hydropower and some policy requirements. We did a survey and review of national policies in several countries. Of course, this was quite fresh in 2020, and maybe there has been some changes now. Things are happening fast with the Renewables Directive, the EU taxonomy, and of course gearing up for nature protection in Europe. So, but still we did some work on this, looking into not only the Water Framework Directive, but also other and national policy requirements. So I'm soon about to wrap up. The idea with FitHydro was actually to provide solutions, methods, tools, and devices, and policy requirements, and also effective tools that can be used for planning and design to make hydropower more socially acceptable and environmentally sustainable. And I think the idea of making these tools available also perhaps makes it also necessary to do some training or adaptations in each country to them. And this, I hope, is going on, but as a EU project, FitHydro is of course ended, but you can still find all the information in this FitHydro wiki, which we are maintaining here at SINTEF actually. So we also had quite a few stakeholder workshops and so on, so to try to make FitHydro outcomes and results available not only for hydropower companies or authorities, but also for other stakeholders. And I'm not sure how much it has been used. It would have been interesting to find out, but still we don't know that. So you can have a look at the FitHydro wiki and see what you find there, and hopefully it will be useful. And what we have done since then is, of course, using some of the solutions, methods, tools, and devices in Norway and other countries. But what we also do now, as you will hear later today, we are kind of combining and building upon what we found in FitHydro and XFlex Hydro to create a new project, which Anton also mentioned, which is called ReHydro, on the demonstration of sustainable hydropower refurbishment. So it goes more into the technical details and things like XFlex Hydro did on improving the flexibility of hydropower and combining with a lot of the environmental sustainable solutions from FitHydro. We are implementing that in 5 demonstration sites across Europe in ReHydro. So with that, I thank you for the attention, and yeah, I guess questions will be afterwards, Anton, so keep them in mind, or of course you can also drop me an email or ask me questions outside this webinar. Thank you.
Thank you very much, Atle. Yes, everybody is invited to write questions directly in the chat, so at the end we will have time to discuss a little bit these questions and perhaps also other suggestions. So thank you very much, Atle, again. So I remember very well, just before the lockdown, there was a workshop you organized on the wiki of FitHydro, January 2020. So I think that was the last time I traveled before the lockdown started. So I have a very good remember very good the Fit Hydro project because of that workshop, which was very successful at that time. So now we go to the next presentation. It's on the project X-Flex Hydro. It will be presented by Elena Magnoni. So she leads the research project group at EPF's technology platform for hydraulic machines. And she lectures also in mechanical engineering, of course, turbine design, I guess. And she holds a PhD from EPFL and worked also at Johns Hopkins University and at NTNU. She is also vice coordinator of the European Energy Research Association's Hydropower program. Thank you very much, Elena, and I give you the floor.
Thank you very much, Professor Slice, for a nice introduction. And hello, everybody. I'm pleased to provide you my presentation about the outcome and beyond of X-Flex Hydro project. Okay. So hopefully you can see my screen.
Perfect.
Yes.
Okay, excellent. Okay, so the context in which this project was framed is clearly within the energy transition and the boosting of hydropower role and hydropower technology to be ready to tackle the challenges of the future for the power system's stability and reliability. As you know, so there are critical changes in the power system in terms of both requirements from electricity demand, electricity supply, which will double by 2050 in respect to 2020 values. And also there is an expected increase of intermittent generation capacity, namely coming from wind and solar to meet the renewable energy targets of the energy transition goals, which is going to be 5 times increasing in 2050 in respect to 2020 value. In this context, of course, there is a strong requirement and need to endorse flexibility and reliability of sources which are controllable, such as hydropower, and which can provide so all kinds of energy flexibility and power flexibility to the grid. So provide ancillary services, but also storage capability for the long-term flexibility. In this context, our X-Flex Hydro project targets the innovation and demonstration activities through 4.5 years in order to develop new technologies and integrate those technology into existing hydropower, new and existing hydropower station to demonstrate which is possible to strengthen hydropower flexibility while keeping reliability of the technology. In this context, so X-Flex Hydro gathered together 17 partners from both academia and industry in order to envelop together innovations, demonstration, and deployments of those solutions. So you can see here the main steps of our project, started in 2019 and concluded in February 2024. First, by drawing what are the flexibility requirements and capability of hydropower, then understanding how smart solutions targeting, for instance, digital tools can improve hydropower flexibility, which are the 6 demonstrations that I will show you in the map in the next slide, and overcoming basically all different kind of hydropower stations that exist worldwide, so pump storage, reservoir storage, and run-of-river power plants, and then how to deploy those results. So drawing road paper and guidelines, analyzing what can be the potential and uptake to markets and the dissemination. The consortium, as I said, is made by mainly 17 partners, including academic industrial partners. There had been 4.5 years project for a total budget of roughly 18 millions, funded 15 millions by the European Commission. Technologies that were developed are mainly 4, adapted then to all kind of hydropower station to showcase their capabilities. So the first technology demonstrated is a variable speed, both full-size frequency converter and doubly fed induction machines, to show not only the extension of operating range capabilities, but also the strengthening capability of reducing fatigue and improving lifetime of equipment through transient operation, namely startup and stop sequences. Hydraulic short circuit, which is so a simultaneous pumping and generation in different units for the same pump storage power station, increasing operating range. Hybridization with battery energy storage system, so putting a battery within the same hydropower station in order to have a faster response and faster capability to answer to the grid requirements while reducing wear and tear on turbines, so reducing number of movements. And finally, digitalization tool, we call it Smart Power Plant Supervisor. But so would be digital solutions integrating knowledge and modeling, advanced modeling of the main parameters driving decision-making parameters of a plant operation within an optimization framework. Auto solutions, depending on the case type, specific case study, was demonstrated into mainly 7 demonstrations, plus in our laboratory at EPFL, at the technology platform for hydraulic machines, where we also had 1 test rig demonstrating preparing those technologies, fine-tuning those technologies before being fully demonstrated on the plant. So we had in red 3 demonstrations in Portugal, a storage hydropower station, and 2 pump storage power plant featuring reversible pump turbine, 2 demonstrations in France, Grand Maison being a pump storage power station with ternary groups and reversible pump turbines. Sorry, not ternary groups, with Pelton units and reversible pump turbines, so being quaternary groups. And Vogelgrün being a run-of-river with Kaplan and a battery, which is now in operation. And 1 demonstration is Switzerland, Smooth being reversible pump turbines with full-size frequency converter capabilities. I'm going straight to the results. So first of all, we were able to draw what we called the ancillary services matrix. Ancillary services matrix that you can see in this picture, and allows through numerical simulations and further through demonstration to evaluate the capability of each technology implemented within each demonstration to provide specific ancillary services. So you can see here they are listed in terms of time response, so from sub-second response at synchronous inertia up to what was called the tertiary frequency reserve, which is now called replacement reserve. So in the order of magnitude of several minutes, plus voltage capability, support capability, and black start. And the matrix assessed, as I said, in respect to the baseline, which is the first line of each of a demonstrator, the improvement or relative improvement in providing such ancillary services and the participation to the corresponding markets, which are at the bottom in each country, for each implemented technology. I invite you for more detail. Of course, here I don't have time to explain you detail what each number stands for. You can see already the color, so the dark green means that there has been a major improvement in respect to the baseline, red where there has been no improvement because the technology was not targeting that specific improvement. And I invite you to go on our website in xlexhydro.com to check exactly the capability of those results in terms of supporting the grid flexibility. The other major results was the development of a digital tool, the Smart Power Plant Supervisor, that was successfully installed in all demonstrators. And this is an optimization tool that allows to use meta models built on the simulations, numerical simulations and experimental tests at both reduced scale and full scale, in order to define a health index and optimize operations of units based on the evaluation in real time of such an health index. Both modeling techniques and optimization algorithms have been published, so are open source, and then each manufacturer have been developing his own proprietary solutions to be exploited on the specific demonstrations. And so these also led to commercialization of the results of the projects. Going to the demonstration. So first, for pump storage power station implementing hydraulic shear circuit, this was demonstrated in Alcheva, Gramaison, and Fradesh. We have 3 different demonstrations because each one has feature and particular capabilities. For instance, Fradesh were particularly interesting to study how variable speed with a full-size frequency converter plus an hydraulic shear circuit could achieve a full extension plus from a negative power to positive powers and vice versa without stopping operation, and also by performing fast changes in modes. So for instance, we achieved to demonstrate that it's possible to change and switch from pump to turbine mode in only 70 seconds for a machine of several hundreds megawatts. In Gramaison, we had Pelton plus reversible pump turbines, so quaternary groups. And here also, thanks to the hydraulic shear circuit and fixed speed machine, we were able to significantly raise the capability of regulating and pumping mode into these power plants. And here, for instance, you can see the operation since September 2021, when this was put in commissioning, and the extension of the operating range was reached in the first 6 months of operation. And for Alcheva, it was again a different case study, still with hydraulic shear circuit, but this time fixed speed reversible pump turbine, where the challenge was mainly the stability of the machines. And here you can see some nice numerical simulations where those unsteady flow numerical simulations were performed to verify the limits of operation of hydraulic shear circuit in terms of head. For what concern the integration of technology solutions with low capex solutions in storage hydropower station, it was successfully demonstrated that by only implementing the Smart Power Plant Supervisor, we were able to fully extend the operating range up to almost a few percent at deep partial load for those Francis turbines. This was mainly done by performing extensive studies experimentally in our reduced scale model testing at EPFL, coupled with numerical simulations that draw really the limits of operation and estimate not only the performance yield chart, but as you can see in the slide, also a damage yield chart targeting a limit in terms of hours of maximum operations that specific machine would be allowed to operate at that particular load and estimate the corresponding damage. So thanks to this digital tool, which is now fully operational on site, the operator knows the risk that they have to operate at partial load, a deep part load, raising the damage. They know the performance, and so they can evaluate and support the decision whether they want to participate to markets at such stretched operating range at partial load. Demonstration, the third technology that was demonstrated was the hybridization with a battery energy storage system. You can see here in the picture the container. If you drive close to the Rhine River, close to Vogelgrün, you might spot such a container where the battery is installed in the hydropower station. And the main purpose of this study was to demonstrate a battery size that is out of a compromise between the least cost and the higher capability to support the Kaplan unit, but in this case was a 35 Kaplan unit, although with several maintenance issues, to still fully support primary frequency control. So one of the fastest at the order of seconds for the markets, still in a run-of-river condition, and minimize at the same time the number of movements of blades and guide vanes. So you can see here, for instance, that for producing and participating to the same markets, the Kaplan unit will need to do without the battery those number of this mileage. So in terms of movements of the blades and in red, and of the guide vanes in green, while with the use of a battery, by using different control strategies, this could be cut down up to almost 8%. And we show, it's not in this slide, but if you use even more developed and advanced control algorithm, for instance, by using a model predictive control algorithm, that could be cut down to almost 95% of a number of movements of guide vanes and blades, by still keeping the same number of cycles for the battery and the same participation to the markets. So that was an overview of the technical results in terms of the activities that were developed in the projects. Furthermore, as you might remember, we said that there are innovations, there has been 7 demonstrations, and there is a phase of deployment. So the next slides, I will show really briefly how we performed this deployment and which tools are available for further deployment and of the results beyond the duration of the project. So now, first of all, we drew a white paper, a technical white paper, which is free. You can download it in our website, where we detail how we developed such technologies, how we implemented that on site, with all the different specific activities we were required to achieve results. And we have another roadmap and recommendations, so for the industrial deployment of those technologies, focusing more on the market aspects and policy aspects for the use of such technologies. Both, as I said, are publicly available on the website of the project. Overall, so now if we want to draw some guidelines and we want to take something out of the projects and the results of the projects that we got, so what is in those 2 documents are guidelines specified by kind of hydropower stations in order to set a first, let's say, indication and roadmap about the modernization of a given plant. For instance, if you have a pump storage power plants, here are the different considerations that we did, the different applicability of a study that we could ensure within our framework, our project. Here we have the different possible solutions that can be expected that are needed to overcome flexibility. And here the different hydropower technologies that can be implemented to support to succeed in overcoming such issues. So for instance, in SMUT, I mentioned before that's a full-size frequency converter new unit, reversible pump turbine, where one of the major issues was how do we fully exploit the variable speed beyond the fact of being able to change the speed to actually compensate head variation, and so having a more efficient operation at different head values in respect to the nominal one. And what we studied is mainly how can we leverage variable speed in order to find the path during startup sequence that minimize the damage. And here you can see, for instance, all possible trajectories that we have been investigating, of course, by respecting the plant conditions, the water hammer limits, so the penstock and hydraulic layout limitations. And here you can see within the characteristic curve of a machine about which kind of of performance and target operation we are talking about. Putting together 1D numerical simulation, 3D numerical simulation, and validation in our test rig, plus then validation demonstration on site, we were able to find path and trajectories of startup sequences and we were able now to say to new potential plant how to do that, and realize startup sequences that are in the order of less than a minute, and also comply with the damage that is up to 15 times lower in respect to a standard startup sequence employing a synchronization with the grid, so in case of synchronous machines. How did we try to evaluate and to put, let's say, our results into a quantification about this extension of flexibility? You might remember at the beginning of my presentation show you one of the innovation part, which is evaluation of how different technology can provide ancillary services in terms of participation to ancillary services and related markets. We did a kind of same evaluation, but this time by evaluating the key performance indicators. So we identified the extension of operating range, the response time, the ramp up and down, the need of maintenance, the plant efficiency, and digitalization level of the technology that was required. And this was evaluated for fixed speed, but also for all different technology that we implemented in each site. So you can see, for instance, the results of such an evaluation of the key performance indicators for the pump storage power plant. We did the same thing for storage power station. So in this case, for storage power station, we studied only Francis units power station. And here you have a major challenges to be overcome for flexibility improvement. And our solution, so either variable speed and or the digital tools such as Smart Power Plant Supervisor. And here you can see the same kind of assessment in terms of key performance indicators. So which kind of performance indicator can be improved thanks to each technology. Same thing for run-of-river power plants. Here the applicability, the challenges that must be overcome for flexibility, and possible technologies that Xflex Hydro proposes as a solution. And each technology, which kind of improvement can provide for flexibility performance. I went quite fast. That's mainly because I invite you to download the technical white paper and see in detail why and how we can achieve such result by implementing each of these technology in a specific scenario, in a specific hydropower plant with similar conditions. So this leads me to my last slide with the major takeaways. So Xflex Hydro propose several technological solutions that can be adapted to all kinds of hydropower stations, and their performance can be assessed through the ancillary services matrix in terms of performance in the markets, and key performance indicators in terms of indication of how flexibility can be improved. Those are flexible solutions and provide, depending on the needs and the ancillary services requirements and opportunities, new scenarios and new venues for hydropower exploitations, and all guidelines for flexibility deployment are provided by the project, and hopefully we hope to see new project and new power stations following such a guideline for new equipment and modernization. So with this, I thank you very much for your attention, and I'm looking forward to take your questions.
Thank you very much, Elena, for this very detailed presentation. I remember also the very successful workshop you had. It's now, I think, just 1 year ago.
Exactly. It was exactly 1 year ago, yeah.
There were a lot of interesting presentations and also a huge amount of discussion ongoing, also with people from the practice. So I think that's also a project which has quite a significant impact now in the hydropower sector regarding flexibility. Okay, thanks a lot. We will see if there are some questions later. And now we go to the next presentation. It's on the project Hydropower, and Ingo Ball, Senior Project Manager at WIP Renewable Energy, who coordinated this project and contributed also to our hydropower research and innovation agenda, where you can see the very nice YouTube on the link which we have presented now in the chat. He has a background in sports sciences, so good that you are not skiing today, that you are among us. And of course also in renewable energy management, and he has worked on multiple EU-funded hydropower initiatives, including Restore Hydro, EAMP Hydro, focusing on digital optimization of hydropower plants. Ingo, the floor is yours. Thanks.
Yeah, many thanks, Anton. So I will try to provide my screen. So let me see. Can you see the presentation screen?
Yes, we see, Ingo.
Yes.
Perfect. Okay, so many thanks to the colleague from ETIF Hydropower for providing the opportunity here. I see that Emanuele has also now joined the presenters group here. Mille grazie. Oh, grazie mille, how you need to say, also for inviting us. So I will write you through the Hydropower project and will make you aware of the tools that we still actually have available for the sector. The Hydropower project was another project than the two ones we had before, not that deep into technology, but let's say more together with international colleagues. Just working together for the sector. So the first part is the outline, of course, some information, general and the structure, the objectives that we have had and the impact we like to achieve, but the most important, of course, the tools that are still available for use. And at the end, I will share with you some, let's say, messages coming from our target countries, from the colleagues from there. So the full project title was Hydropower Solutions for Developing and Emerging Countries, Hydropower in short. We were funded within the Horizon 2020 program and had a budget of almost 3 million euros. We started in beginning of September 2019, originally planned to have a duration of 3 years, but then as the other two projects, the pandemic more or less hit us hard. So we asked for an extension of 9 months and had a total duration of 45 months. 13 participants coming from 11 countries, which you can see here now on the slide. More or less half of the project partners came from Europe, and the other half from our target countries in Africa, from Cameroon and from Uganda, and in Latin America from Colombia, Ecuador, and from Bolivia. The main aim of Hydropower were to support the European hydropower industry, how we like to bring the best tools from Europe and the know-how to our Latin American and African partners, and enable thus more technology export for European companies. And at the same time, of course, we like to stimulate energy transition in developing and emerging countries by making this market uptake support, which we like to have as a win-win situation and focusing on sustainable and locally adapted solutions. In concrete objectives, this meant some mapping efforts of putting on, let's say, paper the European hydropower industry, mapping more than 2,000 potential hydropower sites, as well as stakeholders in the target countries, preparing then framework analysis of and for the target countries, organize capacity building activities, worked then on 15 case studies, three case studies per target countries, We also were setting up then an online platform, providing sector information and enabling contacts, of course, have organized B2B workshops. And at the end of the project, we had a actually very nice study tour by invited guests at different hydropower organizations and companies in Europe. The structure is here the typical work package structure of a project. What you can see here was more or less special is that we had a work package bundle, work package 3, 4, and 5, where basically all the project partners of the consortium together were working in a way to achieve the goals. We set us as well some impacts and numbers. So for installed megawatts in all the target countries, we like to trigger off in total 90 megawatt, which in theory would then amount to an additional EU investment in these target countries of 136 million US dollars, according to our calculations then. And of course, in the countries, we like to contribute to different objectives, increase the rural electrification, for example, in Bolivia, in Cameroon and Uganda as well, of course, but there also the urban electrification has been an issue. And in Colombia and in Ecuador, the increase of the share of renewables was the objective, either putting out the coal in Colombia or replacing the fossil oil in Ecuador. And of course, with the activities, we also like to make the pool of hydropower experts bigger in the countries. And once these projects that have been looked at should be realized, then of course this will lead to more local jobs. But now to the tools that are still available for use. I have put here 5 bullets. The first one is the handbook about the European small hydropower technologies. We're more focusing on smaller hydropower solutions. This handbook is available in English, Spanish, and in French. You have here the URL and can, of course, still download it. Actually, thanks to the colleagues from Fit Hydro, we also have had some support from the colleagues, and we have one chapter about from the Fit Hydro project in this handbook. So you find information about small hydropower systems, overview of hydropower system components, then the development process, and also, of course, important, the project finance for international small hydropower projects. The next tool would be then the capacity building course. We had actually during the project life capacity building courses, as you can see here on the slide, for Bolivia and for Ecuador, and also in Africa. On the left part of the slide, you can see that the very first part of the capacity building had to be online due to the pandemic, let's say, impact. This capacity building course is actually ongoing. We have an online capacity building course provided by our partners from IHE Delft. This is still open, and if you click on the URL that you can find at the bottom of the link, you still can register and try to make this capacity building. The next tool would be a replicable pre-feasibility study. Within the project, we were actually working, as I mentioned, on 15 different pre-feasibility studies. Started first with project developer workshops, discussing with the Latin American and the African colleagues what basically would be the best sites and which ones should be assessed. And once that was done, then there have been excursions in Africa, Cameroon and Uganda, as you can see here, and of course also in Latin America, where our experts sometimes had to climb high mountains and then make their way to the jungle. But finally, they provided these 15 pre-feasibility studies. However, we like to have one replicable pre-feasibility study. So this is an extra document. You can find here as well the link to download. This replicable study is a 50-pager containing a general, let's say, instruction how to make a general regional description, the site description, how to address hydrology and sediment transport, layout alternatives, then how to make the project description, also use a feasibility check and risk analysis, and of course, at the end, some recommendations. The next tool would be then the so-called Hyposo platform, including these pre-feasibility studies. Let's say a screenshot of the Hyposo platform you can see on the right of the slide here. It is basically a meeting platform that is open for hydropower stakeholders who are interested to join the platform, and they can set up a profile there and get in contact with each other. Then also via this platform, you can access the Hyposo business cases. And last but not least, also have an access to the Hyposo map. So here you can see an example of such Hyposo business cases. Those are 3 examples from Bolivia. And as I said, get in contact if you're interested to find out more about these cases. And the last but not least tool that we have developed is the so-called Hyposo map. So now I need to ask Iraya or
yeah, I will share my screen and I will showcase the video.
Okay.
Okay. So you see my screen now. And now I will play the video. Okay, here we go.
Okay, I see just, okay, so now here we just jump into the Hyposo map. Basically, yeah, you can see this, you have several layers, altogether more than 40 layers that can be viewed and also, let's say, combined. 5 main categories: operational hydropower, climate and hydrology, hydropower resources, background and infrastructure, as well as base maps. You can, let's say, have a look at different layers on the maps, gorging stations. And of course, this is relevant information if you like to develop hydropower plants. Also, where are the transmission grids located, and other key information. You can see also that at the bottom on the left, up on the left, and that is available for Bolivia, Colombia, Ecuador, Cameroon, and Uganda. It is of course very quick, but just giving you the impression what can all be done with the let's say with this tool. This was basically just the information about the mean annual flow, I think. Now it's going on with I think the catchments or the climate zones. So the cursor is still looking for the next function, but should be there in the next seconds.
Can I go forward or should I stop?
It should
okay,
actually,
now it's
yeah.
going.
Okay, it's moving again. Okay,
Sorry.
Great. So basically, here you can see that these dimensioned 2,500 potential hydropower sites, together with their key data sets, can be shown on the map. Yeah, by clicking on them, you find more information. As I said, of course, the protected areas are important to be considered. And yeah, the gorging stations in combination to get the best information for your planning of the plant development. And in addition, of course, the precipitation that you have there, plus the let's say different kinds of maps that you can display. The map are available, and that would be in short the Hyposome map. And now I think I need to regain the screen.
Yeah, I will give you now the access.
Mm-hmm.
Okay, here we go.
Okay. Yes, and yeah, for further information about the Hyposome map, here's the contact of one of the masterminds behind it from Lithuania, Linas Jurevicius. So feel free to get in contact with him if you want to find out more about this tool. And not to forget also, of course, we carried out framework condition workshops in our 5 target countries that led to policy recommendation papers that are available. And for the 15 cases, also a financial assessment is available for download. And if you're interested, also some videos to look at. But also finally, from our friends, from the Hyposome friends from the countries, I got some messages, for example, from Cameroon. They're basically the funding of the selected 3 projects is still a major issue. So you're invited to have another look at the studies for the sites in Cameroon. And what our colleague from Cameroon also is highlighting is that the dissemination of the untapped hydropower potential should be given, let's say, way more importance in his country. The contact, if you like to discuss these issues further with him, is given here, Mr. Joseph Kenfak. And yeah, if you have a budget in your organization, we are still looking for budget for setting up a workshop in Cameroon where we can, let's say, look into more detail for the stakeholders in Cameroon into the Hyposome map. From Colombia, I was in contact with the site owners of the potential plant named Palace. These site owners are looking for receiving either offers or support, and think that a third party to develop the project would be best. Please, for further steps, contact Mr. Gomez Echeverri. From Bolivia, I've already shown the 3 potential sites. You can either get in contact with Mr. Ledesma or Mr. Gonzalez. And a nice update from Uganda. Actually, there our potential projects are already being worked on, and which was one of our, let's say, missions or objectives, is that European partners are involved. Regarding Ecuador, you can get in, let's say, you can write me if you like to get a contact enabled. This I will then follow up. And this would be it from my side. If there are questions, of course, I'm happy to answer them.
Thank you very much, Ingo, so for this very interesting presentation and also this impressive tool. So I think that's very useful in many of these countries. So now we have some time, 15 minutes for discussion questions.
Before the questions, if Emanuele, if you want to say some words, we give you the floor.
I would like also to welcome Emanuele. So he is the chair of this cross-sectional working group who organizes these webinars. Normally he did some introduction from the European Commission point of view. Now, Emanuele, we are happy that you are among us also for the discussion, and if you have other informations.
Yeah, thank you, Anton. Hi, Ingo, Atle, Elena. Also, hi to Janire and Niraya that are also supporting us from a technical perspective, which is very important. Sorry for being late, but I had urgent institutional activity at the beginning, so I could not join from the beginning. Anyway, I think that by means of active hydropower is very relevant to keep alive the already finished and concluded projects, because they may have important data, important information and advice for policymakers, and also for the ongoing Horizon project. and they are anyway linked also to the current programs at the European Commission. For example, I'm thinking to the IPOSO project that is aimed at increasing the export capacity of European companies toward other countries. And this is very important, especially considering the current geopolitical situation where Europe and the European Union must be more competitive at the global scale. I'm also thinking, for example, to the project Fit Hydro, X-Flex Hydro, presented by Atle and Elena, that aimed at increasing flexibility and sustainability of the hydropower fleet. So they are all very relevant programs and projects that also fit inside the current program of the European Commission. So even if they are concluded and finished project, they are still alive and must be still alive in supporting and stimulating discussion. So thank you very much.
Okay, thank you, Emanuele. So I don't see if we have questions. Iraya, do you see?
Yes, we have questions. First one is for Atle, and the question is, they were asking, Guillaume Keiser was asking what type of turbine was used when you were doing the presentation. I don't know to which specific slide was he referring, if the person want to speak.
Sorry, was it about the kind of turbine used for the sensors we put through the turbine?
Yep.
VDS, yeah. If it's so, it was low head turbines, couple turbines or one bulb turbine, and the idea is that it has it's slow rotating and large blades, so it was actually a big chance for fish to go through without any blade hits. So we were mostly worried about temperature pressure drops and so on. And it seems like we estimate that 95% of the fish would survive in the tests we have done in this with the Kaplan turbines. I hope that answers what you asked about. I'm not sure, but
yeah, he
I'm
responded. Thank you for the clarification.
So Atle,
responded.
Your €1,000 device survived going through the turbine, I guess.
Yeah, they all survived very well, and we used them many times. We download the data and put them through again. So, yeah.
Next question is for Elena. Are there any follow-up projects to X-Flex? I found the project highly innovative, and it would be great to know if you're planning to build on achieve results. Additionally, how can companies participate in these efforts?
As Atle presented, we currently have follow-up projects, both Fit Hydro and X-Flex Hydro, which is ReHydro. And in X-Flex Hydro, the environmental considerations were quite limited because it was really focused on technological development to put the scientific basis to move forward on hydraulic machinery technology modernization, and in the overall, of course, hydropower system. So now we are building upon those results in ReHydro, in particular on the hybridization case study, to expand the capability of hybrid units by considering also environmental concerns about the environmental model, such as the one developed in Fit Hydro, and also managing water and the water viability. We are also integrating a new digital tool considering environmental parameters, considering, for instance, sediments, erosion, etc., within this smart power plant supervisor framework. And overall considering, for instance, refurbishment for variable speed pumping units with an environmental aspect. So we know now how to develop new units, making out the most of this variable speed capability. And we are studying, for instance, in ReHydro, what happened to the environment when we introduce such new pumping capability and variable speed capability, changing flow conditions, causing, for instance, hydro peaking, etc. So that's definitely a follow-up project, and we hope there will be much more.
Thank you, Elena. If anyone has a question, also you can raise your hand and we will give you the voice. I don't see any other questions here.
Perhaps until we have a question, I have a question to Elena. This short circuit operation is a little bit trendy at the moment. Can you just explain for those who are not specialists what is the motivation to do that and how much energy you lose?
Yeah. The motivation, of course, if you look at the energy, you're clearly right. We lose because we have efficiency of as low as 40% in respect to maybe 80% of at best efficiency in generation or pumping. And the reason to do that is to enable pumping regulation capability. So pumps works on off, especially if they don't have variable speed capabilities, they consume a given power depending on the head conditions, and that's it. So you cannot participate to power regulation if you are in pumping mode, because you have just one power we can play with. Introducing hydraulic short circuit means that you simultaneously generates, so you use the turbine, and that allows you to change, so to modulate the power output in pumping mode by changing the total negative power output by modulating the generation power through your turbine, which is dispatchable, which is controllable, because turbines, we know how to regulate them. So overall, we have an increasing losses because it makes a recirculation. So head losses increase through the piping system, but allows you to participate to market and to be remunerated into those markets with pumping power, which of course is of great interest for plant owners and owners of pumping units.
Thank you, Elena.
Thank you, Elena. There's a question here to all of you. It says, thanks to all the presenters. Sorry, my question is: we are talking about classic hydropower, dams, and weirs. What about the conversion of kinetic energy and according technical concepts? Wouldn't now be the time to investigate more towards such wireless approaches? What's your all presenters' opinion, and on what scale could this impact the future of hydropower? I don't know if I explained myself on the question, and who wants to go? It's for the three of you. Emanuele also.
I may add, I can add something, but I give the floor to the others. Maybe.
Yeah, I can start. I can start. The kinetic energy, of course, has a much lower potential in total than conventional hydropower, but it can be very well used in conduits, canals, and places where it's not feasible to build a dam, but it also has environmental impacts as it interferes into the river. However, I think hydropower's role in those countries where it's well developed, like in Europe and North America, is more to provide also flexibility, energy storage, and enable renewable integration. In other parts of the world, there's still a large potential for new hydropower. It just has to be developed in an environmental friendly way. And of course, kinetic hydropower can also be added but it hasn't got the same. It hasn't got the same flexibility and potential to store and balance energy. Anyone wants to add to that? Please go.
Yes, please, Ingo.
Yeah, I could maybe add then, as Atle just mentioned, that for Europe, basically, I would neither see such extremely high potential, but of course, if in some cases it might be a nice solution. But what I've seen in Latin America, in our partner countries that all had, let's say, large regions in the Amazon basin, where it's basically flat and you have a lot of water moving in the rivers and very isolated places. So there, of course, for these places, we were addressed by stakeholders from the countries what we think could be done with kinetic energy, and therefore I would see this also then as a nice opportunity.
You?
Yes, I can also
personally-
add something. Sorry, Elena, go, please.
I just want to say that I can just endorse what was already said, that in a context like Switzerland, where or like overall Europe, where we have clear potential for classical and conventional hydropower exploitation, there will be, I would say, also other more unconventional way to exploit sources that probably will raise more the potential and the share of hydropower. But it totally makes sense for some countries to further exploit, and there are many also research efforts try to develop new concept of those hydrokinetic turbines. So I think there are ongoing activities, especially for in those countries where this potentially is needed.
Yeah, I can add something. Yeah, the European Union, by means of Horizon project, funded some projects on hydrokinetic turbines in the past. I don't remember exactly the name. Could be something like high kinetics, but I can provide more information if you want. I did an assessment at the European scale, and indeed the potential for hydrokinetics in rivers is not so high. It could be good in specific context for European Union, but at the European Union scale, the potential was, I think, something below 1 terawatt-hour per year. Also because you need the flow velocity that typically should be higher than 1 meter per second. And it's not so easy, especially in Europe, to find also the good depth, flow velocity, and available power to connect them to the grid. But they could be useful for local context or also for developing world. And I would also to add something. I think that an interlink among these three projects could be, for example, to exploit the knowledge built by the project of Ingo, IPOSO, to export to other countries the technology that have been tested in the X-Flex and Fit Hydro project in the future.
Actually, just following up, I think I could probably make a newsletter again after the project, but highlighting also the two other projects that have been presented here. Why not?
Do we have other questions, Iraya?
No, I think we are done with the questions. In case someone has more questions, you can reach us and we can also answer via email and contact with the speakers. But Anton, I think you can close so we are on time. I will pass the slide.
Okay, so we are happy that we had again a very nice, interesting webinar. Thanks to our speakers, Elena, Atle, and Ingo. Thanks a lot giving us this information on this project. And it's also always good to have several projects in parallel so we can see the links which have been established or could be established in future. So thanks a lot to all. So we will go on with this webinar. So there will be in perhaps 3 to 4 months another webinar with some other projects. We would like to thank also all who connected online during these webinars. I've seen we passed over 100 sometimes. Then sometimes when people went to go for a coffee, there were a little bit less, but we had a very good participation to this webinar. Thanks a lot for all those who connected. So now I have just to finish with publicity. So that's the last slide. So we will have the Brussels Hydropower Day. It's the 3rd edition, and it will take place on 8th of April in Brussels, of course. And the topic of this year is contribution of hydropower flexibility and storage in the safe energy transition in partnership with environment under climate change. So you see, we will address almost everything what you can discuss about successful hydropower, and we would like to welcome everybody to participate to this third Brussels Hydropower Day. So with that, again, thanks to the speakers. Thanks also, Emanuele, to having connected
You're
for the
welcome.
discussion.
Thank you.
And thanks a lot to everybody, and have a nice late afternoon. Thanks a lot. And for those who have Carnival starting tomorrow, if you can disguise you perhaps as a turbine. That would be nice. I didn't find such a disguisement, but perhaps that would be a good idea. Okay, thanks a lot, everybody.
A turbine or also as a fish?
Okay.
A turbine or a fish?
Yeah, that's right. Okay, thanks a lot, everybody. Have a nice evening.
Thank you all.
Thank you.
Bye.
Thank you. Bye-bye.
Bye, everybody.
Bye, bye, bye.
Bye.